Welcome back, folks. In this pre-work, we're looking at our double angle identities. And I want to give you a reason why we're interested in these double angle identities. The first question is a little bit of a silly question. I'm asking, can you immediately factor this expression, the sine of 2x minus the sine of x? And the answer is no. They don't contain any similar factors, so no common factors. It's worth pointing out that although they both use the word sine, if we take on a value for x, maybe this would be if x were equal to 10 degrees, this would be the sine of 20 degrees, and then we're subtracting from that the sine of 10 degrees. And these are not like terms. While they are in some ways related, I don't know of any algebra way to simplify this expression at first glance. So why do we mention that? Because here I'm about to solve an equation that has that expression in it. So we're trying to solve the equation, the sine of 2x minus the sine of x equals 0. And we're on the interval 0 to 2 pi. And the problem is that I'm stuck, just like I was stuck up above here. I don't know what to do with this expression. But there's a hint. Let's use the double angle identity sine of 2x is equal to 2 sine of x cosine of x. So I'm going to replace the sine of 2x in this expression right here with that double angle identity. And when I do so, I get 2 sine of x cosine of x minus the sine of x needs to equal 0. And look at how this has improved our situation. Before, there was nothing we could do. We said there were no common factors, there weren't like terms, there was no way to combine these two expressions or do anything with it algebraically. But now, if I look at the pair of expressions here, 2 sine x cos x and sine x, we see that we have a common factor of sine of x. So let's factor out that common factor of sine of x, which would give me sine of x times 2 cosine of x minus 1 equals 0. And our situation is now greatly improved because we can now apply the zero product property that we discussed in class, and we can set each factor equal to 0. So I'm going to set the sine of x equal to 0, or 2 cosine of x minus 1 has to equal 0. For each one of these two equations, I'm going to draw the unit circle and answer the question, where on 0 to 2 pi is the sine of x equal to 0? And that happens here and here. And so that would happen at x is equal to 0 and x is equal to pi. Careful, folks, this is not the case. But if this had been a inclusive bracket, then we would also include 2 pi. But that's not what we have here. We just include 0 and pi for our answers. For the second equation, we have a little bit more work to do. If we isolate the cosine expression, we get the cosine of x is equal to 1/2. And if I were to go draw the unit circle picture for this problem, we want to know where's the cosine value equal to 1/2, and that's up here and right here. And if we take then 0 to 2 pi lap around, we would hit that point right here at pi over 3 and again at 5 pi over 3, giving us the two answers, x is equal to pi over 3, 5 pi over 3. So that gives us a total of 4 solutions. It's polite to give them in order to your reader. Oops, that's over 3 and pi and 5 pi over 3. So kind of an interesting problem where we solved a trig equation for the angles that made that sentence true. But here was the thing. When I gave you this problem, there was nothing we could do with this problem initially. When we had the sine of 2x minus the sine of x, we were stuck. And what came in to help us? This double angle identity that the sine of 2x is equal to 2 sine of x cosine of x. So I think the right question to ask is, okay, I see that if I have an identity, I can solve for the various missing components, but where did these identities come from? So one thing I'm going to ask you to do in this class on this next exam is I want you to derive some of these identities. So we're going to let's derive this identity first the sine of 2x equals 2 sine of x cosine of x. Let's see why that's true. So let's give it a shot here. Let's start with the left-hand side here. So I'm going to start with the sine of 2x, and then I'm going to do some legal mathematics. So one thing I could do, and this may not be immediately obvious, this is why I'm teaching you this, I'm going to rewrite the number 2x as x plus x. So I can write that as the sine of x plus x. Now, first of all, do you believe me that's true? If I were to combine the x plus x in here, I'd have 2x, okay. So I believe that that's true, but why do you do that? And I will say that in this case, I know from experience. I've worked this problem a handful of times. But I would also say that in the last unit, we learned our sum of two angles identities. And so I'm trying to maybe capitalize on some of my existing knowledge. So I rewrote 2x as a sum of two angles. Then I'm going to go ahead and use this formula from the other day that said that the sine of alpha plus beta is equal to sine alpha cosine beta plus the cosine of alpha sine of beta. So I'm making use of this identity from our last unit. And here, what's kind of interesting is both alpha and beta are going to be the letter x. So here, alpha equals x and beta equals x. And I'm just going to follow this formula. So let's give that a shot. When I do so, we would have the sine of x times the cosine of x plus the cosine of x times the sine of x. And this is not important to keep track of this, but if I said, okay, this x, which is playing the role of alpha, I'll underline it. There's where it showed up, and there's where it showed up. And if I double underlined the x that was playing the role of beta, there it is, there it is. So you can see I filled in the correct values, substituted them in. Okay, look what we have here, though. Even though one x is playing the role of alpha and one x is playing the role of beta, they're the same x, and we've got the sine of an expression, cosine of that expression, plus the cosine of that expression, sine of that expression. These two expressions, this whole thing and this whole thing, are the same. And so we're adding them together, so that would give me 2 times the sine of x times the cosine of x, which is actually what I wanted, so we'll stop there. That's equal to 2 sine x cosine x, with that last line being redundant. I didn't need to write it. Okay, so let's return to this problem here. In this problem, we were asked to solve this trig equation, and we were stuck. We couldn't move anything around. I mean, I guess we could have added sine of x to both sides, but I was stuck. I couldn't algebraically move forward, and so I pulled out this double angle identity. And the question that we asked was, well, okay, that's fine, but where did that double identity angle come from? And here I've derived it for you. So one of your essential skills is to go ahead and memorize this identity that we just used, because you never know when it will come in handy. And it does come in handy in your Calculus 2 course especially. Okay? So go ahead and commit that identity to memory. I would recommend putting the identity on one side of a flashcard and put on the other side one of your double angle identities. When we come back to the next video, we will continue working through these double angle identities. We'll see you next time, folks. Bye-bye.